spots in the first section. Or 281. Anyway, so the thing to do is if you're on the wait list, come back, stay here, right? Then come back on Tuesday. Because the last day to drop without a W or before the census date is Sunday at 5 p.m. And so, what's going to happen is if people drop or get dropped between now and then, because this is the last class until next week, when you come in on Tuesday, we'll do a retroactive add to fill in those spots, okay?
So don't go to the last day.
Right, yeah, so if you're not registered, you can't go to the lab, but we'll make it up. It'll work out.
They have holes in them.
Those ones from the bookstore?
Yeah, I just wanted to make sure that.
These are fine. They're just fine.
I was just making sure. Yeah. Won't break them.
I know, right?
Wasted $10.
He's like, oh, it's everywhere.
$10 Googles.
They're venting, but they're splashed.
You gotta zoom in one more. There you go.
What's that? Didn't open up.
Oh.
I got $1. I got $1.
I'm broke. I'm gonna go to the bank after this, drop some money.
But so he's chapter homework right now. What chapter is he on? I was like chapter 2. That's like chapter 2 homework.
Oh yeah, I tried to do it.
That's chapter 3 or 2.
We just started before we ended class last time.
Did he already start chapter 2?
Yeah.
He finished it?
He finished 2 already.
And
You started here. Over here.
I did the introduction to chapter 3 last time.
Yeah,
We just talked about energy
Quantum theories, right?
and units and stuff like that. Section.
Don't tell me.
I got $1. I'm not gonna edit out these words, man. It takes too much time.
So we're going to do
If I was to upload this on YouTube,
He's recording.
it's recording.
nature of light.
Like 2 minutes and 30 seconds.
If I upload this onto YouTube, I have like gonna edit this out.
And when we say light, most of the time, most people I think of
That's clear, right?
visible light, that you can see with their eyes. But light really means electromagnetic radiation. And what electromagnetic radiation is, it's weird is what it is, but the way to start thinking about it is as a wave, really a three-dimensional wave, with two components. I can never draw this. There's a picture, what I'm trying to draw is figure 3.3 in your textbook on page 61.
3.3, don't do it.
When you look at just one dimension of each component of this wave, there's an electrical component and a magnetic component.
Equation?
Oh no. Figure 3.3.
Figure 3.1. Figure 3.3?
Is it this thing? No, that's 3.4.
I think it's this one.
Yeah, this one right here.
Yep, right there. Precisely.
And the two components of electromagnetic radiation are perpendicular to each other. They travel through space. It's a wave traveling through space. And the electrical component is going up and down in this direction. Then the magnetic component would be coming out of the board towards you and going back into the board. So this is supposed to be, they do a better job of it than the book, but perpendicular to this, right? 90 degrees.
Oh yeah.
light, electromagnetic radiation, at least when it's in a vacuum, moves at a constant speed. Speed of light. And at least to 4 sig figs, is that right? They give the exact number in the book, but this is 4 sig figs, that's sufficient for you guys. Should memorize that?
90-degree way? 90-degree.
From electrical
From
part.
electrical.
Oh, from electrical.
Yeah, so if this is the black one is the electrical component, the blue one being the magnetic component will be coming out of the board and going back into the board.
Okay.
So this is the value of C that I want you to use 4 sig figs. Most of the time, constants, I go 4 sig figs. Your book gives you the exact value in there, but then they only use 3 sig figs. So just be aware of that. They give you a picture that's probably useful to know. On page 60, they give the range of electromagnetic radiation from radio waves down to gamma rays. And if you look at, well, if you have your book, if you look at that picture, you'll see that they have 2 scales, okay, as they're showing the full range of electromagnetic radiation. The first thing to notice is that visible light is such a really, really small portion of the entire range, right? It's all electromagnetic radiation. It's all light, really. But visible light is just I mean, you know, it's a very, very small portion. It's only from the wavelength, and I'm going to talk about that, is only like 400 to 700 nanometers. Whereas the range goes from like a kilometer down to 10 to the minus, what? minus 10 to the, well, they only go to 10 to the minus, oh, yeah, 10 to the minus 12 meters. So, because light acts as a wave, you need to know a few things about waves. And in general, there's a okay, in this equation, this is the what's called the frequency. Okay. This is the wavelength. I'll define these for you in a moment. The speed of any wave is equal to its wavelength times its frequency.
Well done.
The wavelength, if you pick any portion of the wave, the next time you see that portion of the wave, say the peak, very top of that, the distance between the 2 parts is the wavelength. We could pick the trough, we could pick where it crosses the axis going down, so here to here. It's all the wavelength. The frequency, it's pretty much, I think the way to think about frequency, at least at first, to get an intuitive picture, is imagine standing and having a wave wash over you. Water wave, doesn't matter. Like, you know, any wave. As it hits you, if you count how many times, say, a peak or a trough, doesn't matter, hits you per second or per minute, per unit time, that's the frequency. How many per time? With this stuff, we do per second, right? Units we use for wavelength, the meters or some form thereof. Frequency, it's 1/seconds, inverse seconds, which you will also see as this or this. HD stands for hertz, and hertz just means per second. So just looking at the units, meters times 1/seconds gives you meters per second. That's unit of speed or velocity. So if you look, if you have your book, if you look on page 60, what you'll see is that they have the wavelength in nanometers, right? That's, in chemistry, we deal with the light that we deal with most of the time. It's in the nanometer range, 100 nanometers up to like 1,000 nanometers, pretty much. And if the top scale, if you look at the wavelength, it goes from, on the left-hand side, where the gamma rays are, 10 to the minus third nanometers, which is 10 to the minus 12 meters, all the way up to 10 to the 13th meters, right, which is really long. 10 to the 13th nanometers. So at the gamma ray end of it, it's a really, really small wavelength. This distance here is short. Up at the radio wave end of the spectrum, it's really far apart. About like a kilometer, 1,000 meters. If you look at the next scale, which is frequency, on the left-hand side, where the gamma rays are, the really short wavelength, it's a really high frequency. The number of waves per second is like 10 to the 20th. And as you go to the right, the radio waves, the frequency gets smaller, right? I mean, yeah, like 10 to the 4th per second.
Oh, okay. So you can see
So-
it's going up here on that, right? And the
What
blue
that's
one's just
showing
one.
is what this equation shows here, and that is that there's an inverse
It starts growing
relationship
bigger.
It's like
between
like
the
that. Closer to
wavelength
this one? And then closer
of
to
the
that.
wave
Kinda like
and the
that.
frequency of that wave. As one gets bigger, the other gets smaller, and vice versa. So long wavelength means small frequency. Short wavelength means high frequency. One of the reasons that scientists, when they started thinking about light and electromagnetic radiation, thought of it as a wave is the double slit experiment that they show right there. What happens in the well, first of all, in general, waves. What happens with waves? If you imagine just a water wave, this is probably a really good analogy to have in your mind. If you imagine a water wave traveling along and it encounters a barrier, right? If it's just a solid barrier, it's going to hit the barrier and bounce off, right? But if you put a hole, a slit, in that barrier, what's going to happen is when that wave hits, where the slit is, the water or whatever the wave is made up of, it's going to go through that slit, and it's going to spread out in circles as it comes through. So,
You can still accept my phone. Wikipedia. Watch yourself. I've been watching him for a while now.
A bit. Stalker.
No, I thought it was pretty exciting the way he was doing it. Peter Tom, no.
I think she's referring to this picture.
the wave traveling
This
hits
picture.
the barrier of the slit. What happens is that the slit starts spreading out like this. Where you might think of where the line is a peak, and in the middle here a trough. Peak and a trough. That makes sense to you guys so far? And that's fine. With light, if you shine into that slit, you just see a bright light back over here. Say you put a detector, a wall, right? Something where you can see the light. Shine light through here, you just see a bright spot right there. No big deal. Then, if you put a second slit in this barrier, okay, I'm going back and forth between light and regular waves. Now, going back to just regular like water waves or something. This is going to do the same thing. Traveling up. When these two waves interact with each other, where they overlap, if a peak lines up with a peak or a trough lines up with a trough, you get constructive interference. The peak gets higher, the trough gets deeper. On the other hand, if a peak of one wave lines up with the trough of another wave, they cancel out, and it's flat there. That makes sense to you? So where they cross here, they're lining up, and you're getting, increased amplitude. Where they're opposite, they're canceling out. With light, the same thing happens. And the way that we know that that happens is when we have this wall here, and we look at the pattern that the light makes when there are two slits in this barrier over here, we get a series of light and dark lines, which are constructive and destructive interference. Where the waves of light, electromagnetic radiation, line up, the peaks and the peaks and the troughs and the trough, it gets brighter. Right? More amplitude means brighter light. Where the peaks and the troughs line up, it cancels out and it's dark. There's no light coming through that. Well, it's canceled out. That makes sense? And so this is wave-like behavior, and this is how we started out thinking about waves. Later on in the chapter, we're going to see how we can also think about light as not just a wave, but we could also think about it as a stream of little tiny packets of particles, little BBs shooting through space. We'll get to that in a little bit. So that's constructive, destructive interference. That's a double slit experiment. Yeah, they have a much better picture, of course, on page 62.
Yeah. You didn't notice? Pretty stopping already.
Oh. Not quite. What you're thinking about is electrons shooting them through, and there's a double slit experiment done with electrons.
Yeah, minimum.
And what happens there is the electrons can detect whether or not
Precise.
whether or not there's another hole.
That's where the lines are.
Okay. On to section 3.3.
I don't think even Jackie Chan knows that one.
Hey, Jackie Chan disciple.
Yeah, man.
Jackie Chan will kick our ass. Oh shit. Let's get this book over a little bit.
It's all about that body weight creation right now.
It ends up, and you guys know this from your everyday experience, that when you heat up a piece of metal, for instance, it glows. The hotter you heat it up, when you change the temperature of it, its color that it emits changes, right? When you first start heating it, it might go orange. As you get it hotter and hotter, it gets white hot, right? It goes white. Scientists are trying to explain this. Before we knew about quantum mechanics, or right around when we knew about quantum mechanics, and they were trying to use just classical mechanics, just regular, classical physics. And they were able, and what they were trying to do was they were trying to get a relationship between the temperature of the metal and the wavelength of the light that's mostly given off. And they could do that with one equation down at low temperatures. And they could do it with another equation up at higher temperatures. But they didn't match up. It was called the Great Wildcat, or the UV catastrophe. Right? It just blew up. The equations didn't match reality after a certain point. And that means there had to be something wrong with the equations. nobody was able to figure this out until they proposed quantization of the energy of, well, quantization of energy. Mark is this.
Wait, this question.
E equals HW or HV.
Yeah, no, H. It's,
What he said was that the energy can be described as some constant called Planck's constant.
I know.
Times the frequency, times a frequency. Frequency can be continuous, but a constant means that that the energy is only going to come in certain chunks, multiples of Planck's constant. Right? It's Planck's constant times this, or 2 times Planck's constant times that, and so on. Planck's constant H.
God bless you.
6.63 times 10 to the negative 1.
Ooh, you missed.
This guy took 4 sig. That's what I want you guys to know.
Oh, wow. That's very good, too. Oh, that's huh? Let's see.
6.62 times 10 to the joule seconds.
You get into Planck's constant.
This one only goes up to 3, but okay, 6.
Really?
Remember, joules
Yeah,
is the unit of
it
energy,
stirs.
kilogram meters squared per second
Yeah,
squared.
he's smart.
Okay. Okay, little
So,
Psychedelic, super
Planck didn't
smart.
have any idea how this could be. He just knew that when he made this assumption, that he was able to come up with an equation that described black body radiation successfully in all regions.
crazy.
Then came Einstein. And Einstein was attempting to explain another phenomenon or experiment that classical physics had been unable to explain. That is the photoelectric effect.
Oh man, damn, this thing is going to photo electric effect.
Man, that's why this equation that we're not
E
getting
photon
to
equals HV. So, almost the same thing.
It is.
The way the photoelectric effect works is this. The picture is on page 64.
Go, page 64.
Basically,
Right there. That picture.
take a piece of metal, and all metals will do this. And you put it inside of a vacuum, put it in a glass container that where you pull all the air out, pull a vacuum. And usually what you want to do is you want to put an electrode inside of there too, and hook it up to the outside so you can see. You hook them together, and what you want to do is you want to see when there's a current flowing between the two. I'll tell you why. So, you guys get out of that picture. You have just a piece of metal sit inside that glass tube. You have an electrode, just another piece of metal, also in the glass tube. No air, no gas in there, nothing. It's enclosed. It's closed. And there's a wire basically connecting the piece of metal here and the electrode. And usually you put a meter in between the two so you can measure the current or flow of electrons. So you start out, nothing's happening. And the reason that nothing's happening, there's no current detected, is because there's no connection right between the metal and the electrode. It's not a complete circuit. Right? Then you can take light. And usually you want to use just a specific wavelength or frequency of light. And you shine it on that piece of metal. Then we're going to turn a knob and we're going to change the wavelength, so change the frequency of that light. When you let's start out at long wavelengths, right? It's low frequency. Hit that metal. Doesn't matter how bright the light is, nothing happens. And that didn't make sense because, let me tell you why. As you adjust the wavelength of the frequency of the light, shorter and shorter wavelengths, you reach a point, and this point is different for each metal, but you always reach a point where all of a sudden you start seeing a current. And what's happening is when that light hits the metal, it ejects an electron. And the electron gets pulled over to the electrode, and now you have a complete wave. Okay, you guys kind of get the picture of what's going on there? The reason that doesn't make sense, okay, if an electron is going to be kicked off, the reason it didn't make sense to them with classical physics is that when they took that light, the longer wavelength light that did kick an electron off, no current, they tried shining really, really bright light of that wavelength on the metal, right? And that bright light means higher amplitude. There's more light hitting it. More light means more energy. Classically, there should be enough energy to kick an electron off if you make that light bright enough. But no matter how bright they made it, nothing happened. On the other hand, once you hit that spot where you get the wavelength short enough, it doesn't matter how dim the light is. You can make it as dim as you want to, and you're still going to kick an electron off. The brighter it is, the more electrons that you kick off, but you always kick electrons off. Classically, this doesn't make sense. Chase.
When you say kick off an electron, do you mean like kind of start a flow of electrons?
Oh,
Or just knock off an electron?
hit it,
Exciting
and if the
electron.
light hits here, this is what they knew at that time. Light hits here, electron comes out here. Right? That's it. We're going to talk about that electron. We have an equation that describes it a little bit and all
But
that.
of course, it's the flow of photons, so that there will be flow.
Well, we're
of
not
electrons.
photons yet, see? We're still treating it as a wave. Right?
Because it's in the vacuum, it gets we'll get to it.
That'd be crazy.
But you guys with me so far?
So the electron is coming from the
Metal, from the metal. The metal is being, when I say kicked off from the metal, you know, the metal is a bunch of atoms, right? Say iron or gold or what have you. And each atom has a nucleus and the electrons. That's where the electrons come.
So this is constantly happening, right? Just like at a rate, like an
But
electron.
once you hit that
This seems pretty
wavelength of light,
Right.
as long as you're shining that light on that metal, electrons are being kicked
Kick
off.
off, try to, just like different rates depending on how quick
No clue how to do
Yeah, that's
it.
right. Einstein came along, and first of all, yeah, so they couldn't explain it. It didn't make sense with classical physics. And he said, what if, this is where we get to photons, what if the light was also quantized, the energy of the light was quantized? And he said if it's quantized, that's where we get to the packets, right, the little packets of energy, of light. So we call them a photon.
Photons. Oh, photons.
And he used Planck's constant. He found out that Planck's constant is the one that describes that. So now it made sense. Well, after he did some explaining. Because if we think about now as this light, instead of a wave, which is why it didn't make sense, because they were thinking about it as waves. When they started thinking about, when Einstein started thinking about the light as being this stream of particles, photons he called them. And each particle had a certain amount of energy. And it was a discrete amount of energy. It's quantized. That's why the word quantized, right, means a chunk, right? The energy is quantized. It can have only certain values, right? Multiples of Planck's constant. So this, as a stream of photons hits that metal, each photon as it hits, either it has enough energy to kick off an electron, or it doesn't. And you think about down inside that metal, what has to happen? We haven't talked about really electron configurations or anything yet, but basically what has to happen is that photon hits the metal. It has to have enough energy to pull or to knock an electron away from the nucleus. There's that attraction between the nucleus, positively charged, and the electron, negatively charged. It's being held there. So you have to put enough energy in to pull it away. If that photon doesn't have enough energy, if you think about it, this as a stream of little tiny particles, each one hits. If that one doesn't have enough energy to kick an electron off, to remove it from the nucleus, nothing's going to happen, no matter how many of those photons, okay? So when we talk about brightness, okay, we can think about it as the number of photons that are hitting, say, per second. Doesn't matter how many are hitting. If each one of them doesn't have enough energy, nothing's going to happen. But if they just come in really, really slowly, right, one photon at a time even, each photon, when it hits, if it has enough energy, it's going to kick off an electron. Okay. Doesn't that make sense to you guys?
Can they keep doing it until there's no more electrons to kick off, or would that be like impossible?
Well, there's
Some attraction between that and the nucleus.
they're being replaced. This is a complete
Oh,
circle,
okay.
right? So they're coming back in, right?
I remember.
Also, when they
You're asking for the
force
impossible.
on the electrons from the proton to the nucleus, it's stronger than the nucleus
Alright.
less. It was
So-
really to balance the scale.
This equation here is
Stop sounding
really
so
important.
smart.
Hey man. Yeah, for that second, it's
Just get the
stronger than
memorization in. Oh, they don't wait.
Yeah.
This tells us that the energy of light, of a photon of light, is directly proportional to the frequency of the light. So the higher the frequency, the higher the energy. And it's inversely proportional to the wavelength. So the longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. And you saw that in the spectrum of electromagnetic radiation in the textbook. The long wavelength of light was the short frequency and low energy. Going back to the photoelectric effect.
Professional camera person.
The kinetic energy of that electron that's kicked off. Einstein figured out, is equal to the energy of the photon that hits.
Yo, I think the
They
testing
don't use this simple, I think, but it doesn't matter. There's something called the work function, minus something called the work function. This work function just describes the minimum amount of energy that will kick an electron off from that metal, and it's different for each metal.
Man, this is on the
To
test.
pull off the, yeah. Yeah, I remember this stuff. This is on the test. Extensively memorized this thing.
It's the Green Lantern. Green Lantern's gonna kick our ass.
Looks like the Green Lantern symbol.
I didn't know he was a fan. Is he a fan? Is he a fan? Is he a fan of Green Lantern?
Oh, well, he could be. Did say he liked superhero stuff earlier. He said he was kind of a nerd. Which is a surprise to that.
So when the energy of the photon, the minimum energy photon that will kick an electron off is the energy of the photon that's equal, whose energy is equal to the work function of that metal. And when that's true, when the energy of the photon is equal to the work function, then the kinetic energy of the ejected electron is zero. It doesn't have any kinetic energy. But as the energy of the photon increases, the kinetic energy is more. The kinetic energy of the electron increases. Right? If the energy of the photon is less than the work function, then the equation tells you the kinetic energy is negative, but really that means that nothing gets kicked off, right?
Okay. Then the kinetic energy of the electron would be zero.
So it's nothing.
Yeah, I understand completely. It's different. It's different for the females. So you basically have to figure out double function for each one if you're trying to figure out what's the weight,
The three possibilities, either the energy of the incident photon is less than the work function, equal to the work function, or greater than the work function. Less than the work function, nothing happens, so it's just electrons ejected. Equal to the work function, that's the minimum energy photon that'll kick an electron off, and it does so, but the electron has no kinetic energy. And then as you increase the energy of the incident light, the kinetic energy of the ejected electrons increases by this equation here, which is just that.
The frequency of the photons, does that change for the different types of metals, or is it all
The
the same?
the
It's
work
different
function
for
changes
every metal.
to not different metals, right?
The
So
work function.
we adjust the frequency of the photons with our laser over there, right?
Yeah.
So we're using the laser because what a laser is it's going to shoot a collimated beam of one wavelength or one frequency light. So this light is coming out of the light bulbs up here in the sun. Has a lot of wavelengths, a lot of different frequencies of light in it. We want to do this experiment, so that we can simplify it basically. We want just one kind of light, one color, one wavelength, one frequency. And that's what a laser does for us.
And it changes per metal.
So what changes per metal is what frequency or what wavelength of light will just kick off an electron. Does that make sense?
Yeah.
Also,
So we're next to KE electron.
Here?
Now go up to
I
the.
forgot what I was saying.
Kinetic energy.
How would you measure the wavelength of the light?
With the meat.
Measures energy.
Okay.
We're going to do some calculations here.
Calculation.
We certainly aren't going to measure it like I showed you here, but measure one thing to the next.
Yeah.
I want to calculate.
I mean, yeah, if you accept that equation there, then you just measure the.
It's in his book.
That's my book.
All right, so let's do some calculations. Then we're going to start out simply just calculating wavelengths, frequencies, or energies of different kinds of light. And then we're going to come over here and do a few calculations with light attention.
Go right to blue.
Which
What?
blue?
Oh yeah, just leave.
How about this?
Yeah, you could. Sorry.
It's gonna be on there. Let's have that. Oh yes, the case is that side. You think about this is a fun class.
It's true, it is.
I'm about to break the icebreaker. Talk to random ass people.
Yeah, dude, I meet a lot of cool people here.
I know, huh?
Like Samsung. It's cool.
Okay, thank you.
It's cool, whatever. After you download an acid race.
What is the wavelength of a photon?
You guys got your calculators?
Yes.
Please, get them out. Figure this one out real quick. Use the value of C that I asked you to memorize. And value of X.
What's the wavelength?
C, which is this. Wait, what are we looking at again?
We're looking at that one right there. C equals wavelength times frequency.
Oh, okay. So you just rearrange the equation when you take the light energy.
Oh, light energy is that one there. E photon. Right there.
Photon? That's
So we're trying to find the wavelength. It'll just be what's lambda again? I forgot.
yeah, lambda is
Lambda is 7.23. Yeah, 7.23 times
I thought
10.
E photon was at 7.3 because that's when that you.
No, because you're trying to solve for the oh yeah,
You're solving for the wavelength, exactly.
Yeah. In nanometers.
And once you get the wavelength in nanometers.
So it'll be 2.998 times 10 to the 8. We would have to use Planck's constant too, right?
Yeah, Planck's constant.
So 6.22, 6.626 times 10 to the negative 34 joule seconds.
Like the wave, like light, is it like a whole bunch of particles in a wave, or is it like a particle?
And then stream. No.
So it's like this.
Oh, you got a smart calculator, right?
Yeah, I do have this one.
Put it
It's
in.
not that much smarter than
Oh, look at your calculator, look at that.
It's fine.
The answer is that it's not a wave and it's not a
7.23.
It's
C is
it's took me a long time.
Yeah.
It ends up
So we-
we're going to get to more electrons.
oh yeah.
That's an ugly ass wavelength sign. Alright, Julie, did you solve it yet?
Electron actually.
The formula we use is
So what is it? It's 9 to 1. It's just and it ends up
So much. So then we got.
I don't know, are we using the right equations? We're solving for E photon, right?
No, we're not. We have E photon. We have energy of light.
a lot of people. Einstein had it.
We have
All
no.
right, you guys get a number? No?
Give us a minute.
A minute. I already gave you a minute.
Ah.
Give us another minute.
Come on.
I don't have a smart calculator, so I can't do it. I set it up, that's the only thing I can do.
So that is the equation you guys were using, right?
Yes.
And which variable?
Yep. Wavelength.
Wavelength, which is lambda.
Lambda.
Your range is?
I set it up, but I can't.
Just get that.
Mhm.
H is constant, 6.626 times 10 to the negative 34 seconds. C is speed of light, 2.998 times 10 to the 8 meters per second. And the energy of the photon is that number right there. We have to do this. But I want to make sure you guys are doing the exponents and all that correctly on your calculators too. So, go ahead and actually plug it in, please.
When you're solving for 14 light,
And then light energy, which was
but since you said,
2.998 times
since
10
all you do
to
is just recognizing
the 8,
I don't know, my calculator sucks, so I don't want to use that calculator.
which was the light energy 7.23
And if I had to do my calculator, I
times
would
the
have
negative 18.
I did just that fast.
Let's see what we get.
The way the units work out, joules cancel, seconds cancel, you get meters, that's good.
Meters.
How many is nano? 9?
Hmm?
Is nano 9?
Nano is
Nanometers.
9.
Negative 9?
-9.
Mm-hmm.
I'm pretty sure it's just going to be 6.626 times 10 to the negative 30. Oh snap, 4.
2.998 times 10.
You guys get that number for the wavelength in meters? It's not nanometers yet.
Time out. 7.23. 10 to the negative 18.
Wait, did you get 8 or 9?
That's some here.
Okay, perfect.
There, 2.7 times 10 to the negative 8.
Yep.
Oh, we got it. We're on the spot.
Cheers.
We're gonna get an 8. We're gonna
27.5
Hopefully we're not getting.
Oh, dude, come on, don't give up.
You guys get that number?
my number stops at 7.
Yeah, my calculator.
Yeah, I
My
feel bad for him.
calculator just stops right there.
It stopped?
Well,
It stops
look,
at 7.
it's like .00.
Oh, you know what you should do is You should put it into scientific mode.
Come on. Sorry, different.
There. And go over to scientific.
Oh, that's a sexy shot. Thank you for facing it.
You guys are so weird. That's cool. That's cool. That's cool. That's stop it.
You know it's not cool.
And little sister you've never had.
No.
Yeah.
Damn it.
And then correct.
Wow. God. Wow.
Sam the youngest.
Oh my gosh. I am actually understanding all this from last semester.
I probably didn't. I wouldn't have gotten this last semester. I mean, I wouldn't have gotten the answer right. I would have done something wrong.
You probably know how to set it up, but not do
Rules and then seconds.
It took me a while to find the equation to use.
it. No, because right when I looked at it, I already knew which equation to use. I was like, wow, it just clicked me. It was like, wow.
Wait a second. Where did the seconds and top cancel?
Yeah, it does cancel. All you get left is 9.
With what though?
But see how I said joule second right there? And this second.
Yeah. Wait, but wouldn't that? Aren't they multiplied? Wouldn't it be seconds squared?
Yeah, you're right.
See?
You're cheating.
I don't know what's going on here.
Alright, so do we agree on the number?
How did you cancel the seconds on the joules times seconds?
This is joules times seconds, meters over seconds.
I told
Oh, there.
See, if you.
I feel smart.
Yeah, I keep forgetting.
That's why I look at my notes.
I don't want to.
You're going to go back and forth between
I don't know why I was
wavelength,
thinking it would be
frequency, and
multiplied.
energy of
Wow.
photons all the time, right? Yes.
Why, on the top,
The sig figs.
yeah, where the,
I crossed those in units that I canceled out. I showed you how the units work out. This was joules times seconds, which is the unit of Planck's constant.
I'm feeling
So
better
it
now.
started out like that. And all I was showing you is that. I was just showing you how the units work out in meters here. The joules here canceled with the joules here. The seconds here canceled with the 1 over seconds there. And we're looking at meters, that's all.
What? It was zero.
Nano means times 10 to the negative 9.
oh, okay.
This is the conversion. This conversion here.
How do you get 27?
I got 2.5 times 10 to the negative 8,
No,
so it's like.
divided by that, you got 27.5.
Oh yeah, you did the last conversion, so you put nanometers in there, you know?
I forgot how to do the last part of conversion because when I put it in the calculator, I was like,
Oh, did he transfer it for scientific notation for you?
yeah.
Yeah.
Look. 7475, right? Times 10 to the negative 8. I'll show you put parentheses.
Bazing.
Hold on, okay, look at this.
Wait a second.
1 times 10 to the negative 9.
Because that was the part of my problem before. I didn't know.
Look! 27.5. Yeah!
But it has 3 sig figs, so it's 27.
Yeah, 27.5. 3 sig fig.
Nanometer.
Yeah, 27.5.
What? I'm too excited for this chapter to do on homework now.
I'm gonna start my homework right after this with chapter 3.
And then get to the homework and get screwed up. I did not learn any of this in class.
I'm not gonna lie, for chapter 1, there was a few problems I did not understand.
Yeah, there was. I definitely agree with you. Sig figs.
Yeah.
I got it on twice and I quit.
Are you
What
serious?
was it? Tell me now.
On that problem?
What was
It
it?
helped us when to work on it after class.
I just randomly put spin.
Remember what it was?
Yeah, I'm pretty sure we had the same thing. Like, you know, like, so we can have like a general idea. I got it wrong twice for you.
I think he's he is, isn't he? He's like the body. Yeah, never mind.
Oh, he's writing the questions already.
Yeah, I'm already doing it.
Oh, damn you. Oh, he's doing another example of this? Of wavelength. Oh, never mind. He's doing a different one.
Are required.
That's it, you just solved it.
Are you going to add? Oh, you're gonna be working with work frequency.
It's basically backwards from what
Yeah, we're working backwards this time. Is that substance? Yeah, it is.
Yeah, I mean, sometimes it's a hot dog, sometimes it's a cup of water, right? And to do that, you have to know how much energy it takes, you know, to raise it a certain temperature.
So yeah, basically it's microwave.
So let's just focus on this part of it.
Oh my god.
Can you put a burrito in the microwave? I'm not gonna buy a burrito after this.
Hey man, sometimes I
How do you think we're gonna approach this one?
Work backwards?
sort of.
Yeah.
Sort of, yeah?
Yeah, sort of.
So okay, so
You'll
Yeah,
get,
e-photon.
Yeah, that's E-photon one.
you'll get the.
I think we're using the frequency this time. This is E-photon.
As well,
This is equal to the frequency.
How many photons of wavelength? So what do you mean for photons of wavelength?
No, okay, we're looking for photons. So all we do is plug all those terms in, and then we're gonna be working with the we're not doing this one.
Yeah, we're looking for e-photon.
here, so Kevin's right. The first thing that I would do is I'd figure out how much energy one photon has with this wavelength, right? And that's pretty much the same equation we were just using, E equals hc over lambda. But the thing is, we want this much energy. So all I'm going to do is take this much energy, divide by the energy per photon, that'll tell me how many photons. That's what we're asking for. Does that make sense?
Yeah.
Repeat that, please.
We're looking for energy for a photon first before we can actually solve the equation. Because we don't have. Because every substance has a different energy per photon. We're not sure how much it requires to find the photons of wavelength.
Seems like this on another page. So hopefully I'm just gonna take a whole page on this.
It's just
Well, I'm gonna rewrite this in another book anyway.
to extent.
Should I post this on the Facebook group or what?
Dude, might as well.
Yeah, well, we have all of our voices in here.
Make sure when you're calculating the energy of the photon that if you're not given a wavelength, if you're using the wavelength in meters, that you convert it to meters. I gave it to meters here, but you won't always be given it that way.
What are you thinking?
I was totally thinking .203 was 49.7 millijoules. I was like, where's the J?
Oh. Yeah, because that's the wavelength.
You know, I'm gonna talk to Patel about that one question, that theory thing. I hell hated it. Oh, that stupid theory and law thing was so hard.
Notice the
The
meters
theory law
cancel,
Oh yeah, 3 long.
seconds cancel,
I
and
just
left
quit after.
joules.
Second try, I give up. I was like, no more. I'm not going to be lower than
And
90.
this is
I think I already got lower than 90. I'm like 85 already. I'm like, screw this thing.
the energy per photon.
Joules is energy per photon, isn't it?
Joules?
Yeah.
Per photon?
We don't need to write that, do we?
No, but that's a different energy per photon. So we need that to solve for
But this is like the microwave thing,
photon
isn't
per-
it?
Yeah, we need that to figure out photons of wavelength that by plugging that in with.
So
That
we
means
can
we just
think
have to
about
plug that
this,
equation
the
in.
energy per photon. We can write a conversion factor if we want, saying 1 photon is that much joules. Because what we're basically doing is we're going to convert this energy into photons. You think about it that way. And what I've done here is I've replaced milli with what it means from that same table. Milli is 10 to the minus 3.
Oh, there, I didn't see
You guys
that.
okay with that? So you know, okay, now.
Yeah,
Yeah, sure.
that's a. That's,
I like it better when he said, do you buy it?
Hmm?
I like it better when he says, are you buying it?
It's like as if
When you look at it that way, the joules cancel.
I will buy it, but understand it. That's how I work.
Like that.
I'm lazy.
yeah, that's how I
It's
am.
2.1 down there.
It's not, it's just a 2 with the parentheses.
It's
On the left, remember?
step 1, step 2.
Step one, step.
Two.
It's like
Two.
it's a second. Yeah.
I am buying it now.
Ow, ow, ow. If I totally...
All you do is just divide it. Man, he's working too fast. I know. Give us a chance, Professor Goodale.
I know. I can't even run as fast as he's going. And the joules will cancel out.
Yep. All you get is 10.2 photons,
Photons. Yep.
which is equals to
5.07 x 10.
which is equals to
Photons. That equals
5.08.
5.08 x 10 to the 27.
7.
If you,
It's just dividing this.
this is 22nd, I mean, you know, the exponent, when you divide, it's like multiplying, but you change the sign, right? So it's
I
like
cannot really see.
positive 22 minus 3 is positive 22. So I know the 22 is right. Common mistakes people make with their calculators is they put the exponents in incorrectly. Make sure that you're using, if it has an EXP button or an EE button or a times 10 to the N button on your calculator,
I get it.
you're using that, not just doing 10 to the X. Because there are times when you can, if you put that in with 10 to the X, you'll get the wrong power. That's one thing that happens. Another common mistake here is to multiply accidentally instead of dividing. But I'm fairly confident that if you didn't get that answer, then probably put something in your calculator incorrectly. You can bring it up after class and I'll look at it.
Let's do one with speed of
But
light.
concept, any questions on what you did here, how it worked out? So this step right here, basically, we need this much energy divided by the number of, the energy per photon, and that tells us how many photons we need.
I want to do
I
this.
believe you're going to see something like this in Sapling.
I missed that one in the last exam.
Planck's speed of light plus
No, I'd rather do the work function one.
wavelength.
Let's do a
Work function.
No, don't do it.
using, we're dealing with the photoelectric
Yes.
kinetic energy detector.
Yes.
I don't want to play with Green Lantern images.
I would much be appreciated if he works on that side.
Who does?
What?
Somebody said they had a question?
Oh, I said, can you work on this side of the board instead?
Over here instead of over there?
Yeah. I get a better view on this side.
No, right. There's no way to falsify it. That's why they're wrong.
As far as the way points, so there's heads.
Right by the clock.
It doesn't even matter. It's only Latin. It's gonna pass this equation. This equation is going to cause So this is the photoelectric effect equation.
This is, I need to start the homework as soon as possible. This is off my head.
And so that way it could be extreme. And it would still be away.
You know, I just look at my camera and I just can see what he's writing.
What did you bring
It's so bad.
Ejected.
From a piece of metal.
Ejected.
Work function. Green Lantern.
Yeah, it's a Green Lantern. So green.
That's a positive. That's a negative, man.
Wants to get a leg up, bro.
Dude, I think I missed out on the last recording of the.
Oh, the last equation completely?
Yeah,
It's good, it's whatever.
I hella missed out on it.
I think it's a pretty good battery life. It's able to survive the whole recording.
I still got like 50% left.
Oh, wow.
Yeah, it completely died out on the last one. So I'm paying attention.
So we get photon over here. H plays constant.
Oh, we get the
Well, you
mass.
get it written down, let's think about it and we'll work it out.
9.1 on that. Well, we get a different answer. We just put 9.11 instead of 9.109. If we use 9.11, it wouldn't. Okay, then I'll just use that number.
Because, I mean, if these are two things, you get around and doing that.
Okay, I get it.
He won't.
All right, so, you guys think- what?
That last part, that's the master level.
Yes, the master electron.
There you go.
You're gonna need it, so.
So the first thing I would do is solve for the energy of the photon. My
Right.
bad.
So, okay, so in general, we're talking about work functions and light, and metal. So that's those are the key words that tell you that it's a photoelectric effect. And in general, it's going to be, you know, this equation here.
I hate this equation.
Oh, we're using the same exact one, so.
Yeah, no.
And
That's why I hate the kinetic energy.
just look ahead before you plug anything in or solve anything. You're asked not for the kinetic energy, but for the velocity, right? But you guys know that kinetic energy is 1/2 mass times velocity squared. So really, if we can get the kinetic energy using the mass, we can solve for the velocity.
What's kinetic energy again?
Half the mass.
Times velocity.
Squared. 8K MV squared.
You mean this thing right here? Yeah, I wrote that.
Oh, is that from?
I wasn't sure if I was writing it correctly. That's why.
Yes. the beginning
Oh,
of
last,
yesterday.
yeah, last time.
I mean, yeah, beginning.
Last.
So what I'm showing here, right, so I've just, okay, the equation that describes the kinetic energy of this electron, I rearranged it to solve for the velocity, right? So I took the 2 up here with the kinetic energy, divided both sides by the mass electron, and then I took the square root. You guys okay with all that?
Repeat that?
Sure.
Give us.
Yeah, I rearranged the equation, this equation right here. Multiply both sides by 2. I
yeah,
just
okay.
put this up here, that's why the 2's up there. And I divided both sides by the mass of the electron. Goes right here, that's why it's on the bottom here. And then because this is squared, to solve for velocity, I took the square root of both sides.
Okay, half is the same as.
That's right, yeah. Raised to the 1/2 power. So, what we're going to do, let's set the first step after you realize that this is what you're going to have to do, is get the energy of the photon, because I gave you the frequency, right? But you can get the energy by using E equals h nu. That we give that. I gave you this number right here. So once you get the energy of the photon, subtract out the work function. That'll give us this number right here, the kinetic energy of the ejected electron. Plug in here. Get our answer.
Times 2 is equal to times 2. I have no. It's like a 2.
After you get that number, we have to plug it into the E photon? No, huh?
Well,
We
okay.
have to solve for E photon to get the.
But,
Because that's solved for work function right there, isn't it? Because that equation is for the work function, while that one's going to be for E photon right there.
okay, wait a second.
But why is he using the other, why is he using the wavelength time frequency? He's using the frequency one.
Because we don't have the
Oh,
energy of
land.
the photon yet.
No, he's just doing that. Oh, well, whatever.
Because up here, he's trying to find the energy of the photon, and we.
I thought over here we're looking for the velocity.
We're looking for
We have-
velocity,
We
right?
have that. We don't have wavelengths, so we're using this. So we want to get the energy of the photon,
For the frequency.
so we can plug it in here.
Oh,
that's
what
what
I was. Okay, okay, I know. I get it now.
Time by using H new. You guys get the same number?
You walk too fast.
S negative 1?
Yeah, which is like 1 over S, right? Second units of seconds cancel with your joules. Yeah.
Okay.
From where? Hertz? Oh, hertz means per second, 1 over second, or second to the minus 1. This is just another way of saying hertz.
Oh, I see. Oh, that makes a lot more sense.
You guys get that?
It was just good for the
Ready for the next step then?
Yeah.
Now that we know the energy of the photon, I gave you the work function, let's plug into here.
I'm about to look at the video later to see how you did this part.
So, shouldn't kinetic energy of electron be divided by mass of electron?
That's what I thought too, but then he said what he used to. Huh? What was it again?
Shouldn't, over there it says kinetic energy of electron divided by mass of electron. But over there, there's neither.
No, because that's a different equation that we have to use. That's for the E photon minus, that's the work function.
Okay, that's for later on, but he already got the answer of this one without.
Yeah, without telling us.
Okay.
He was just a step ahead of us.
Okay, so the kinetic energy of electron is 6.38 times 10 to the 15 joules, right?
The kinetic electron energy should be 6.
Yeah, 6.3.
6.38? Well, why you put frequency?
I know, that's what I'm saying. It's like, why is that up there as well?
What is the kinetic energy then? Unless you plug that number into there.
No, I don't.
No, what do you get for kinetic energy? Like, how did he get 7.94?
Which one?
Kinetic energy.
0.9.
No, when you use that equation. How do you get 7.94?
So you get
7.94.
Yeah.
It's in the total.
No, I'm saying like, just remember on the bottom there it says kinetic energy over electron over mass of electron.
The energy of the photon is 4.22.
Yeah.
And you got 7.94. The work function is listed in the
No,
file.
but see how he got the kinetic energy of the velocity? Like, both of the velocity for it.
Yeah, but now
We're
he.
figuring it out. We haven't used it yet.
Yeah,
Oh,
so-
okay.
So right now,
We're just on the first.
So we're going ahead of ourselves, okay.
Yeah, you guys are thinking too far. He's not done yet.
yeah,
Oh,
he's,
okay, we were
he's
thinking
figuring
ahead.
out-
We haven't even used the math.
Yeah, he's trying to figure out the mass or kinetic energy of electron.
Because we were trying to
right
figure
now.
out that big.
Yeah, that is the kinetic energy of the.
So we're just gonna plug those numbers into there.
Okay.
Okay, this makes sense then.
I'll show you how the units work out in a minute, but we're going to get meters per second. Well, what units, if you're looking at them now,
Julie's so
remember that
smart.
joules, another way of saying joules is kilograms meters squared per second squared, right? That's why I want this to be in kilograms down here. Kilograms will cancel. I'll write it out in a minute, right? But the kilograms will cancel, we'll get meters squared per second squared, square roots, meters per second. I'll show you. Let's get the number first.
Page of 31. It's gonna be some. This is the only part where I'm worried about.
So I don't understand why you did that other part first.
I hope he's not done yet, because I'll be super behind if he does.
And that's the kinetic energy of the electron.
2 parentheses? Yep, 2 parentheses. Yeah, 7.34 times 10 to the negative 12.
You had to find the kinetic energy of the electron first. So you plug it into
To the equation, exactly. But,
How's he getting that number?
okay, so
I didn't get that number.
what did this part of the equation have to say?
No, unless I put in the calculator wrong.
Hold on a second. Let me do it again.
Anybody get that number? Did I do it wrong?
You haven't finished the problem yet.
Yeah, I know. You just
Let me
pulled
try it
like,
again.
You know, book for me.
But you said the point, what was it?
This point. What was this purpose?
To find this. So you can plug it
Oh,
in.
wait, okay, so please get that number. If you can't get it, then after class, you bring it later on.
Yeah,
But
I'm not getting
Not
that.
getting that?
Yeah, I'm not getting that.
What are you guys getting?
I'm getting.
So all that time he was looking for this is E photon right here, right? E photon, this part is E photon.
I think my calculator. I'm gonna smack
That's
this
the
calculator
energy of the
upside
photon
down.
minus the electron
Take the square root.
is equal to the kinetic energy of the atom.
Oh crap, I forgot the square root of that.
And it's 2 times.
I got this.
Why 2 times that?
No, I did it right then.
Shoot, because
I forgot to take
remember
square
it's
root
1/2
off.
and you multiply 2 to both sides.
Yeah, I forgot to do that. I forgot to do that. I forgot
Yeah, I
to.
see that. I see that. I'm going from the base function and I'm working algebra. So what I've got reads 1/2 of 9.109 times 10 to the negative 28 times velocity squared equals 3.4388 times 10 to the negative 3.
What?
From there.
Okay, let's, units real quickly. Okay, the way the units work out here, remembering that this is a square root after.
Oh, I got it.
Joules over kilograms.
I got it. I got it. I got it.
So the units look like this. You guys understand what I'm trying to show you? I'm taking the numbers away and just looking at the units. Remembering that joules are kilograms, meters squared per second squared. Remember talking about that, like, last time? Yeah, no.
So the kilograms cancel and you have meters.
No, I got the answer. I forgot to square root it. That's why.
If you forget that a joule is a kilogram meter squared per second squared, just go back to the kinetic energy equation, right?
Yeah.
I mean, 1/2 mass times velocity squared, and put the basic units in. Mass is kilograms, velocity is meters per second, right? And you get kilograms meters squared per second squared, and that's going to be energy, so it's going to be joule. So see the kilograms cancel, square root of this.
See what I'm doing wrong?
Yep, that makes way more sense now.
I got it now. I forgot to square root the whole thing. That's why.
We converted it into grams. No, it is kilograms. Because the kilograms is 6.
So you take 2.
I put -3, not
So,
-30.
that's it for today. If you have a lab today,